Welcome back to our second lecture. Okay, so we will be talking about phase transitions. And that's just, going from one phase to another. Solid to liquid, liquid to gas, gas to solid, so on. These are difficult to discuss in real physical terms because they're another boundary condition. You might remember in the previous lecture I was talking about boundary conditions are difficult. They make things unhappy. Well, that time I was talking about surface tension. Particles at the surface of a liquid are unhappy. That's why you get surface tension. Now, with a phase transition, you're at a boundary, a temperature boundary instead of a space boundary, a boundary in temperature. Okay? And so you're at the boundary between these two phases within a single material. So particles of the solid, say, as you increase the temperature, they're becoming unhappy with being in the solid, and some of them are escaping into being liquid if it's melting. These phase transitions can be difficult to describe in real physical terms, just because you're at a tipping point, at a very extreme place in the understanding of the material. But we won't be going quite that deeply into it. We'll just be exploring it a bit. First off, let's take a look at the terms. I have them listed below. A solid turning to a liquid means melting or fusion. That can be confusing, but that's kind of a quirk of the way enthalpy of fusion was defined. We'll be getting into enthalpy of fusion in a bit. Pretty much no one calls it fusion. It's kind of the really technical term. Pretty much everyone just calls it melting. A solid turning directly to a gas is sublimation. A liquid turning to a solid is freezing or solidification. Sometimes it's crystallization. We'll be getting into that as well in a bit. Liquid going to a gas is boiling. Sometimes it's vaporization. Never evaporation. Evaporation is a different thing. Vaporization or boiling is when you raise the temperature enough that the liquid is spontaneously turning into a gas. The vapor pressure is equal to atmospheric pressure. Evaporation happens below that temperature. Vapor pressure is still happening, but it's less than atmospheric pressure. And for some reason, particles of the vaporized liquid are being, carried away, like by a breeze or something like that. A gas turning into a solid, the opposite of deposition, of sublimation, is called deposition. It's depositing onto a surface of some kind. Sometimes it deposits directly out of the gas and then falls to the ground. That's, snow or hail. Would be a form of deposition. And finally, gas turning into a liquid is condensation. It's forming a condensate. Okay, now seeing it as a list like that may or may not help you, so let's go ahead and switch over to this little diagram here. Just a nice a triangle showing arrows from one direction to another. Fairly straightforward, I should think. Solid to liquid, liquid to solid, freezing and melting. Solid to or liquid to gas, solid to gas, or liquid to gas or gas to liquid, boiling or condensation. And finally, solid to gas, gas to solid, sublimation and deposition. Only this time, instead of putting it in the form of a noun, the name of the process, I put it in the form of a verb. Melt or freeze, boil or condense, sublime or deposit. Okay. So it's the same thing. It's just the processes of the phase transitions. Now, earlier I mentioned that we were going to talk about why melting is called fusion. And that does sound very, very backwards. Well, this is sort of why it is. Okay, fusion should be things fusing together. But it's sort of a quirk of history dealing with the measurement of enthalpy. Hopefully, You covered this in the first semester. Enthalpy basically means heat when you're talking about a constant pressure system. So the amount of heat energy you have to put into something or get out of something to accomplish a certain change of state. So now we're talking about the enthalpy of phase change. So the amount of heat you have to put in to get something to melt is the enthalpy of fusion. But the amount of heat you get out of something when it freezes is also the enthalpy of fusion, just in the opposite direction. Similarly, you have what's known as an enthalpy of vaporization, the amount of energy you have to put in to get something to go from liquid to gas, versus the enthalpy of vaporization being the energy you get back out when the gas condenses back into a liquid. It might help to think of these as reactions. Liquid water turning to solid water. That describes the process of freezing. So it has an enthalpy related to that reaction. Okay, so when liquid water freezes, the enthalpy of reaction is the negative enthalpy of fusion. Okay? Remember that delta, the triangle there, means change. And why is it negative? Well, because when they measured the enthalpy of fusion, they did it for melting, the amount of heat you put in to get solid water to turn into liquid water. So once they'd done that, obviously they couldn't change it. That would just be embarrassing. And so that's sort of what we're stuck with. It works. It works out fairly well. It's not too bad. You just got to remember the sign conventions and the way things work, and try not to get too caught up on it. Now, let's go ahead and talk a little bit about the signs. Okay, if you've studied enthalpy and thermodynamics, you hopefully remember that an exothermic reaction is one that releases heat. An endothermic reaction is one that absorbs heat. So what sign would we expect from the enthalpy of fusion? Now, first we should look at the interparticle distance, how far apart particles are. Okay. So look at this nice handy diagram I have drawn, for the distance between the particles. Okay. Now we have an arrow going from left to right to indicate increasing distance. And we see solid particles are closer together than liquid particles, are much closer together than gas particles. Those three hash marks in the middle of the arrow indicate that we're sort of eliminating a whole lot of space. It's like if this were a number line, it goes from 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's a break, and then 1001, 1002, 1003, and so on. It's just we're indicating that a lot of space has been left out. Gas particles are much, much, much further apart than the particles of liquids or solids. Okay? Remember kinetic molecular theory, gas particles are very far apart from one another, whereas solid and liquid particles are practically touching. Okay? They're right on top of each other. And why does this matter? Well, because particles like being close together. They want to be close together. It makes them happy. They like to snuggle. And that's what enthalpy tells us. For everything out there, solid occurs at a lower temperature than liquid, occurs at a lower temperature than gas. So you have to put energy in order to pull the particles apart, in order to separate them and get the phase of matter to change, first from solid to liquid, then from liquid to gas. You have to put energy in. That means we're talking about an endothermic process. Okay? Going from solid to liquid is always endothermic. Going from liquid to gas is always endothermic. Okay? And the opposite is also true. Going from gas to liquid is always going to be exothermic. Okay? Going from liquid to solid is always going to be exothermic. That is why, for example, the most dangerous part of a pot of boiling water is actually the steam above the pot. Because, for one thing, it's going to be hotter than boiling. Okay, boiling water can only get up to 100 degrees Celsius. The steam can get even hotter. But also because the steam will then condense on your hand, and when it does, it's going to release that heat into your hand, and that's how you get a nasty burn. Okay? It's an exothermic reaction, condensation. Okay? And that heat has to go somewhere. It's going into your hand, or whatever you're holding above the pot of boiling water. Okay. Water that's freezing, you might think, wait, that's cold. How can it be, an exothermic reaction? Well, just because it's occurring at a cold temperature doesn't tell you whether it's endothermic or exothermic. What you have to remember is that energy is moving out of the system into the environment. It's really, really, really cold outside, so the water that that's just sitting out there, it's losing temperature out into the air around it, and that's why it's freezing. The energy, the heat is leaving the water, and the water is turning into ice. And similarly, spring returns, now heat moves back into the water, and you have the endothermic process of melting. All right. So going back to this previous slide, we see solid to liquid is the enthalpy of fusion. Liquid to gas is the enthalpy of vaporization. What is that third one, that question mark? I've left it blank for two reasons. Okay, first off, because I want to make you think a little bit, exercise those brain muscles, but also because I wanted to show you something. First off, the name, hopefully, is fairly straightforward. It's the enthalpy of sublimation. Okay? That's not too surprising. But what might be surprising is the fact that you can calculate it fairly easily. Namely, we're talking about equations of state functions. Okay? That means that, Hess's law applies. Or going from a solid to a liquid is enthalpy of fusion. Going from a liquid to a gas is enthalpy of vaporization. Going from a solid to a gas is just those two equations combined. So what we're looking at is just enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. In an ideal setup. There's always going to be quirks and weird things, but yeah, that's the way it works. The amount of energy it takes to pull the particles of a solid apart to make a liquid, and then to pull the particles of a liquid apart to make a gas, is the same amount of energy it takes to pull the particles of solid apart directly to the gas. It's just the amount of distance separating the particles. Although I would love nothing more than to talk on and on and on about this, I realize that we are getting fairly close to the 15-minute mark. So I'm going to go ahead and call it for this video. We will still be talking about phase changes, phase transitions when we come back, but we will be tying it back into Q equals SM delta T a little bit. We'll also be drawing some pictures. So hopefully you guys were paying attention when it came to energy in, energy out of a substance.